in general, I think, but I have been trying to do that this week because of technical problems people have. I push record again. We may have lost a lot of that. That's
Okay, yes, it shows a red dot up top for us whenever you are.
Yeah, okay, good.
Thank you.
Yeah, thank you. Okay, so if we measure the angle positively in the counterclockwise direction, with its initial point at the origin, initial ray along a positive x-axis, then we say it's in standard position. So a picture is worth 1,000 words here, right? I just need to write the words to make it formal and clear up anything in the picture. Well, you always put we said an angle is formed by two rays, two half lines. If we put the first ray, the initial ray, along the positive x-axis in the xy plane, and then we measure an angle positively this way, you can have a negative angle in standard position, but the idea is that counterclockwise represents a positive measure. And then here's your terminal ray. This could be angle theta. Once we do that, then we'll say two angles are said to be coterminal. This is a definition. If, when in standard position, they have the same terminal ray. We'll say their terminal rays coincide. So it's coterminal, coincident terminal rays. And what we're doing here is we're allowing angles to have arbitrarily many rotations in them now. I could measure this angle in standard position, theta, and then I could measure another angle where I go around 2 times and then come up to here, and maybe that's alpha. And now alpha and theta are coterminal because they have the same terminal ray, even though they have different measures, right? This one went around 2 extra times. So how do you tell if 2 angles are coterminal? Alpha and theta. Well, you have to go around a whole number of rotations, either positive or negative. Whole numbers are the non-negative numbers with nothing after the decimal point. So instead of saying a whole number, positive or negative, we'll say it's an integer number of rotations. Integers are all numbers with nothing after the decimal point. So alpha and theta are coterminal if they differ in measure by an integer number of rotations. Which means 360 degrees or 2 pi radians. If there's an integer multiple of those, then they're coterminal. And it turns out these are very important concepts because when we do what's called trigonometric functions, they'll have the same value for angles that are coterminal. So that's a very important thing that's going to come up. Let's see. So we have problems like this. Here's how you tell if angles are coterminal. You just take the larger one minus the smaller one and see if it's a multiple of 360 degrees if it's degrees, or 2 pi radians if it's radians, right? So suppose I gave you this one. Here's off the sheet here. Are these angles coterminal. Suppose theta equals minus 110 degrees and alpha equals 700 degrees. Are they? Well, you just subtract them. You take the larger one, 700, subtract the other one, minus 110. All right. And you say, okay, that's subtracting a negative. It's the same as adding. So this is 810 degrees. That's not a multiple of 360. Right? This is where it helps to memorize some of these. All right, you take 2 times 360 degrees, you get 720. If you take 3 times 360 degrees, you get 1080. If you remember those, if anything within 3 rotations, you can tell just by looking at it, right? This isn't 720 or 1080, it's something in between. So it's not a whole number of rotations. So you say, no, they're not coterminal. Now, what's more is we can sketch these. And I want you to learn how to sketch these. That's actually a very important thing coming up when we do trigonometric calculations, is to be able to sketch angles in standard position. So let's see what the picture actually looks like so we can see they're not coterminal. Right? To sketch angles in standard position, any angle. Here's a common technique, standard position. First, pull out all whole rotations. This is another reason you memorize these first couple multiples of 360. Then pull out any straight angle if there's one. Then pull out a right angle if there's one still. Then finally, the fraction of the right angle that remains. So for instance, if I want to plot these two and see what they look like, for 700 degrees, this is what I do. I'll say 700 degrees. The largest multiple of 360 that goes into it is 361. So one rotation I'm going to pull out. 720 is the next multiple. That's too big. So I'll say that leaves 340 degrees left over to add up to 700. 360 plus 340, right? Now, 340 still has a straight angle in it. So I can say this is 360, and I pull out a straight angle of 180, and that leaves 160 degrees left, right? So now we'll say, is there a right angle in the 160? Sure enough, there is, right? That's bigger than 90, so I can pull another 90 out. It's 360 plus 180 plus 90, and 70, a fraction of a right angle left over. Now I can sketch it like this. I'll sketch the 360 degrees. Again, since it's a positive angle, I'll go counterclockwise. There's 360. Then I'll go to 180. Then I'll go to 90, right? 90 is a right angle. And then 70 degrees is 7/9. So this is one rotation in this case, one straight angle, one right angle, and then 70 degrees is 7/9 of a right angle. So you draw about 7/9 of the way across, like this, 7/9 of a right angle. And that's where the terminal ray goes. About here like that. And then we'll say this whole angle is 700 degrees. Well, if you're an astute listener here, you can probably see I could have done this a little easier. I'll say this is the way I typically draw angles, is I pull out the rotations, I pull out the straight angle, I pull out the right angle. However, once in a while, you get an angle like this that's almost the last rotation is almost a whole rotation. What would have been easier for this one? Instead of following the basic strategy, you could simply say that theta equals 720 degrees, take away 20, because I remember from memorization that this is 2 rotations. So now I only have to do 2 rotations back up 2/9 of a right angle, right? 20/90 is 2/9 of a right angle. So I could have said 1, 2 rotations, just back up 20 degrees, right? That would have been easier probably. So I'll say there's the basic strategy. Pull these things out one at a time. But if you get something that's almost a whole rotation, you might want to do this instead and subtract. That's the first one. Now let's draw the second one. Negative 110 degrees. That has to go clockwise since it's negative. So let's write negative 110 degrees. Pulling out all the whole rotations. There aren't any because it's not less than minus 360. There aren't any straight angles. It's not less than minus 180. But there is a right angle. So I'll write this as minus 90 degrees minus 20 degrees, minus 110. And now what I have is one right angle clockwise and negative again, 2/9 of a right angle clockwise. So what I'll do is I'll draw a right angle clockwise, followed by 2/9 more. So that's right about here somewhere maybe. And there is minus 110 degrees. So you can see pretty clearly they aren't close to each other, as our calculation predicted. Sketching angles will really help us to be able to evaluate trig functions coming up. So be able to do these kinds of things. Well, that's in degrees also. We also need to be able to sketch these in radians. Doing exactly the same thing. The same strategy applies. It's just you have to memorize all those different things. Right? That 2 pi is a whole rotation instead of 360 degrees is a whole rotation. Pi is a half rotation, a straight angle. Pi over 2 is a right angle, and so forth. So let's try it on this one here. Suppose I said theta equals minus, I'm going to change the problem here a little, minus pi over 9, and alpha, second angle, is equal to 53 pi over 9. Are those coterminal? I guess I should call this B. I'm sorry. I was doing AB. How do I know if those are coterminal? You do the same thing. You subtract the smaller from the larger. You can take 53 pi over 9 minus negative pi over 9. Remember, when you subtract the negative, it's the same as adding it. So I'll say it's 53 pi over 9 plus pi over 9. And now when you add, you have to have them over a common denominator. We're going to do that again and again this semester. They already have one, so we say it's over 9. You add the numerators. 53 pi and pi is 54 pi. Right? So add the numerators over the common denominator. And now does that reduce? Actually, it does, right? 54/9 is 6. So this is actually equal to 6 pi. They differ by exactly 6 pi radians. But you remember 2 pi radians is a rotation. So this is the integer 3 times a whole rotation. You could call this 3 rotations if you like. But once you see it's an integer multiple of 2 pi, you say, yes, they are coincident. Terminal rays, so they're coterminal angles. And we can draw these again. I want you to have practice drawing these in radians also. If you have trouble drawing these in radians in the test, there's nothing wrong with converting it to degrees and drawing them that way. You're welcome to do that, especially when you're getting started. But in the long run, you'll want to be able to sketch them in either degrees or radians in order to be proficient and fast, right? So you don't have to convert all the time. So here's the sketch, just to verify it for ourselves. I'll take minus pi over 9 is already a fraction of 90 degrees, right? So I can sketch that one easily. Pi over 2 would be here. This is a lot less than pi over 2. Here's minus pi over 9. It's about like that. In other words, 4.5 pi over 9 would be a right angle, right? Pi over 2, or 4.5 pi over 9 would be a right angle. So 4.5 of these to get over to here. It needs to be a little less than a quarter. Maybe it's even a little less than that. But it's something like that. It's a little less than a quarter of a right angle. All right, so now I've got that one. I have to sketch it clockwise because it's negative. And 53 pi over 9, I do the same thing as I did before. I first pull out all the whole rotations. So how do I do that? I say, well, 53 over 9, I could rewrite that as, well, I guess let's call it 36 pi over 9 plus 17 pi over 9. Why did I break it up like that? This is actually kind of hard to figure. You saw me hesitate a second. It's because this is equal to 4 pi. It's the largest multiple of 2 pi I can put into this. If I put 6 pi, the next multiple of 2 pi, that's 54 pi over 9. That's too big. So I can say this is 4 pi, 2 rotations. Plus, I can break this up into a straight angle now. I can say it's 36 pi over 9 plus 9 pi over 9 would be pi. There's a straight angle. And then I could say there's 8 pi over 9 left. And so we could say there's actually 2 rotations, that's 4 pi. This is a straight angle. And then this one would be 8/9 of a straight angle. So we can draw it that way. Sketch it as 2 rotations. All right. That's 36 pi over 9 plus a straight angle, 9 pi, plus 8/9 pi. And then you see it lands right here, at least pi over 9 to finish. Once again, since it's almost a whole rotation, it would have been easier to just say this, 53 pi over 9 is 54 pi over 9. That's 6 pi, a multiple of 2 pi. Take away pi over 9, right? It makes 53 pi over 9. That would have been easier. Now I observe it's 3 rotations. Take away 1/9 of a straight angle. So I go 3 rotations back up here, and sure enough, I get that same angle. I notice they're coterminal now. So radians are a little harder to get used to because of these, 2 pi, how do you pull it out of here? But it works exactly the same way. You can either pull out all the rotations, pull out all the straight angles, pull out the right angles if it's convenient, and take what's left. Or you can, if it's almost a whole rotation, it's sometimes easier to subtract. Take whole rotations minus a small angle. Okay. So there's sketching angles and seeing if they're coterminal. If they differ by an integer multiple of 360 in degrees, or by an integer multiple of 2 pi in radians, then they're coterminal, and otherwise not. Let me move the camera over here. Well, it's about that time where I put everybody to sleep. I really prefer 50-minute lectures so you don't get too tired by the end of the thing. So let me put in one more wake up call here. Sometimes you just want to think out of the box on some of these problems. This is a non-math problem. Show that anybody ever seen this one before? This is actually true, but not from a mathematical point of view. And how is that half of that? Well, it's that half, right? You slice it down here. So there's my non-math problems for the day. Maybe you'll be awake to finish here. All right, so now one important application of the arc length is to rotational mechanics. There are all sorts of wheels that turn, right? You have a cable car that moves down the street, and there's maybe a cable that pulls it up, that winds up on this cable, and you want to know how much arc length of cable do I need to make it go so far? Or I have a pulley where there's a dangling cord, and I want to know how much do I need to wind up here, or your kite string, right? You wind up on a coil. Anything that winds up on a circle, we want to be able to do. If it's rotating, how fast is it turning and so forth, not just how much does it let in and let out. So I'll say this, in algebra, you learn that distance equals rate times time, right? D equals R times T. Now, if the distance is along a circle, then we'll call the distance arc length, right? So along a circle, we'll write S equals V times T, using V for speed instead of R for rate. That's the speed that the point on the edge of the circle is moving. It's just convention to use that letter. Technically, you can use what you want, but and then S equals arc length as before. And we'll let T equals time on whatever units you're using. But it's distance equals rate times time, just written for the circle, replacing R with V and D with S. Now, similarly, we can do angles. If we want angles, we can say that theta, the angle that you turn through if you're turning at a constant rate, so angles turned at a constant rate. In calculus, you do variable rates. We'll say the angle you turn through is the angular velocity times time. So this time we'll say theta is the total angle that you turn through. Omega is the angular rate, like radians per second or degrees per second. And once again, T is time. At least that carries over from algebra, right? But you can do the angle swept out by multiplying by its angular. We'll say angular speed here. There's a difference between velocity and speed, by the way. If you take a physics class, in this one and in this one, I kind of don't like these letters because V sounds like velocity, but it's actually, for us, it'll be speed. If you measure along the ground and you're going forward at 2 miles per hour, you say your velocity is 2 and your speed is 2. But if you're moving backwards at 2 miles per hour, you say your velocity is -2 because you're moving in the negative direction, but your speed is still 2. Speed is the absolute value of velocity is the way it works. So we'll write V, but it'll refer to the speed, and we don't want to get mixed up with S, the arc length, right? Now, similarly here, omega will be angular speed. In physics, often omega is used for angular velocity. It can be positive or negative. So I'm just saying that for us, since we're only interested in how fast is it going, we'll use speed. But if you take a physics class, they might use velocity and allow it to be negative, right? So we'll say this is the angular rate or angular speed. Now, what this does is it implies an important consequence. Move this over a little. From our relation we have that arc length is radius times angle subtended in radians only. If I'm turning at a constant rate, I can divide s by t, and I can divide both sides by t, let's say, right? And now what's s over t? Remember, s is velocity times time. So if you divide this through by t, these t's cancel, and you get s over t is velocity, right? Velocity is distance divided by time is what it is, right? So this becomes velocity on this side, or speed for us. And this one, theta divided by t, is the angular velocity, right? This is angle divided by time, just like this is distance divided by time. This becomes v equals r omega. So from the other relation we had that theta equals omega t, we divide that by t and get theta over t is omega. That's a small omega, doesn't look like what's on the Greek houses. We get this relation just by dividing s equals r theta by t. Once again, if you forget this formula, you can figure it out by dividing this one by t. That's what I'm trying to point out here. So this is an important relation between angular speed omega and your linear speed v. What's the difference? When you're on a circle, I'll put it with axes around here. Suppose this is your CD or something, a circle, or the edge is a circle. And a fly lands on the corner, right? The fly, if it's moving around on the disc, now it jumps off and it carries the velocity that it had on that disc, right? It will instantaneously fly off at some speed, even if it doesn't flap its wings, right? It will go like that with some velocity v, right? Or length of the velocity is speed v. But there's also an angle is turning, and omega is the rate at which the angle is turning, and v, the linear velocity, is the speed that the fly goes off at. What this says is if this is turning at a certain number of radians per second, the speed that the fly goes off is r times that. So if you make a radius twice as much, the fly goes off twice as fast. 10 times the radius, the fly goes off 10 times as fast. That's what it says. The speed of the edge is r times the angular speed. Now we can do a few problems here. So suppose we look at this first one here on the homework, 12. A wheel of radius 14 inches. Rotates at 0.5 radians per second. And I should have put something on here, very important, right? This was in radians only that this works. This one works only if, that's for theta in radians. This one works if omega is in radians per unit time, whatever unit time you're using. So once again, you have to use radians for this formula to hold. If it's not in radians, you have to turn it into radians first. All right, so a 14-inch wheel radius, 14-inch radius wheel rotates at 0.5 radians per second. This might be your car tire, right? Might have if it's a large wheel, has 14-inch radius. And then what is the linear speed v? V in the wheel, right? This is important because if your car's wheel is, if you know the rate at which the wheel is turning around and around, you can use this formula to find how fast the car is traveling down the road, right? Because it's the edge of the wheel reels out an arc length. And the arc length is r times, if you can see that still, the angle you turn through. And this, anyway, so if you have an angular velocity of the wheel, v, the speed that you're going at, is r times omega, the rate at which the tire is turning around. So we'll say the car is traveling at speed v down the road given by the radius of the tire, 14 inches, times the angular rate in radians, where we're given radians, so times 0.5 radians per second. Sometimes people use SEC too, but the international units just uses S, so I'll use that when I can. The radians fall out because they are unitless, and we say the wheel is turning at 14 times 0.5 is 7 inches. The car is moving at 7 inches per second. So if you know the angular rate at which the wheel is turning, you just multiply it by the radius. You get the rate at which the car is traveling down the road. So here's the 14-inch wheel, and you're going down the road at 7 inches per second. All right. If this is turning at 0.5 radians per second. That's part A. Maybe I better move this back. Running out of boardroom. But there's the utility of that thing, and there's lots of calculations like that in classical mechanics and if you go into physical sciences. Now, here's another question that's important too. A lot of these turning things are not given actually in radians per second or even degrees per second. Instead, they'll give you in revolutions per minute, RPM. So let's ask ourselves, we want to compare it with some specification for the car. What is the angular speed at which this thing is turning? Not in radians per second, but in revolutions per minute. This is revolutions per minute of the units. How about that? Well, this one, you have to have the following intuition. Theta, or omega, is 0.5 radians per second, is already the rate at which it's turning, right? It's just in the wrong units. You want revolutions per minute instead of radians per second. So what you have to do to convert seconds to minutes? Well, you can write 60 seconds per every 1 minute, right? This is multiplying by 1. Now the seconds cancel, and now I have radians per minute if I leave it right here. But I don't want radians per minute, I want revolutions per minute. So how do I convert revolutions to revolutions from radians? Now I see radians on the top. I can say there's 1 revolution for every 2 pi radians. That's why I wrote all those conversion factors at the beginning. Now I can cancel radians with radians, although you can get rid of them at any time. In order to convert it to revolutions, you have to write this in here. So now what's left is revolutions per minute. That's what I want. So I'll multiply this all out. 0.5 times 60 over 1 times 2 pi, and the units that are left are revolutions per minute. And our chemistry teacher would be proud of us for canceling all these units. Chemistry, this is what you do all the time, is cancel, cancel, cancel units to make sure it's right. And on these problems, it's very helpful too, because they get complicated, as you can see, with units. And 0.5 times 60 is 30. 30 divided by 2 is 15. So apparently it's 15 divided by pi RPM, revolutions per minute. Well, who wants to see an answer like that? The problem in here tells you you should convert this to a decimal, because how fast is that? You can kind of figure pi is a little bigger than 3, so this is a little less than 5, but really this kind of problem, I might ask you to round your answer to 2 decimal places. I think that's what the problem specifies. So here's a very important concept for your calculator. This is my TI-84 here. You can memorize pi, and I think you should. It's approximately 3.14159 is where a lot of people memorize it, right there, 6 digits. And you can divide 15 by 3.14159. I'll give you 100% on the test. But what's, if you're like me and you fat finger it a lot, then it's easy to make a mistake somewhere. It's to be real careful. There's actually availability to evaluate pi to all the digits the calculator can carry right on the display. You'll see a little on the TI-84, a little colored pi, like here it's blue, and pi is above this little caret key here. So you see a caret key like that and pi and blue above. That means I'll push the blue key first and then the pi key, then the caret key, and it will put pi on here to all the digits the calculator has. So on the calculator, I'm going to push this. Let me get rid of this part here. I'm going to push 15. I'm going to push the divided by key, and to get pi to lots of digits, I'm going to push the second key, which is the blue one, followed by the caret key, which has the pi over the top. You may have some other calculator, but they pretty much all have pi over one of the keys. And then I'll push enter to evaluate it, and this does 15 divided by pi, right? That's what I want. So let's try that. Oh, I did. That's right. And then 4.7746, blah, blah, blah. And if I'm going to round it to 2 decimal places, right? That means take 2 digits past the decimal point. That's different than 2 significant digits, right? Significant digits, you start with the first non-zero digit. So this will be 3 significant digits, since I start here, or 2 decimal places. Now the next digit, even though it rounds up to 5, if you rounded it here, since it's not itself 5 or bigger, you just keep this and say it rounds to 4.77. And then what is it? It was RPM. I can put that in at the end. There's my answer to match the back of the homework problems. It's 4.77 RPM is how fast it's turning. You can also convert to degrees per second. How many degrees per second is it? Again, that's still a rotation rate, right? It's an angle divided by time, so it's an angular velocity. So we'll say in degrees, we can also convert it. Omega is equal to 0.5 radians per second. How do we convert it this time? Let's see, it's degrees per second. All I have to do is convert the radians. The seconds are already correct. So I'll just rewrite this as 180 degrees per pi radian. So just like you can convert angles, you can convert angular velocities just by writing the units, making sure the radians cancel each other, leaving degrees on the top. 0.5 times 180 then gives me 90 degrees per second. I'll write it this way. After all, if it does half a radian, wait a minute. Oh, I forgot my pi, 90 over pi. Always do your sanity check, right? So 90 divided by pi, same thing. 90 divided by second pi, I come out with, just rounding it, we'll say it's approximately 28 point, actually, let's write it out. It's 28.6478, etc. This time I can carry 2 decimal places. It's 4 significant digits, and the next digit is 7, so I'm going to round it up and call it 28.65. All right, so this is greater than or equal to 5. And this will now be degrees per second. All right, so in summary for today, what did we find out? Let me move this over. Please do all the problems out of the UCO supplement on section 5.1. Read section 5.1 of the book, it covers this. Look at 1 through 13. We did number 12 right there. It's pretty similar to 13. See if you have any questions on those. We'll do a few more of these next time, I think, on angular speed. But here's what we learned. You can measure angles in radians or degrees. You multiply theta in degrees by pi over 180. And if you forget, just write the units in. It's obvious. Make them cancel to get radians. Multiply theta in radians by its reciprocal, 180 over pi, to get degrees, right? Then we have arc length has the important formula that the arc length S is equal to the radius of the circle times theta, the angle you turn through, if theta is in radians only. If it's not, you just have to convert it, right? So there's an application of radians. The area of a sector of a circle was A equals 1/2 r squared theta, right? Where r is the radius and theta is the angle. In radians, it only works in radians again. Right? You need some more room. Then we said if you have an angular rate of change, omega, the angular rate of change, is theta divided by time, is angular speed, if you're changing through positive angles. Just like speed is distance divided by time, or linear speed, we call it. And then these two are related by V equals R omega, just by dividing this previous relation by time. Also, we have, if we want to convert between rotations, one rotation is equal to 2 pi radians is the conversion factor here, or 360 degrees converts between rotations or revolutions, if you like. And that pretty much summarizes what we tried to do today. Any questions? Okay, we'll try those problems out then. Make sure you keep up. Once you get behind, this stuff becomes very difficult. I try not to space the exams too far apart. Usually I have a quiz in the second week, but we just can't do it online like this. So maybe I'll give an extra credit or something soon. Thank you for coming to class. I'll see you next time.
Yeah. Did you say there was homework listed somewhere?
Yeah, in the UCL homework supplement on D2L. Look up section, download that from the content tab on D2L, and look at the problems in section 5.1 for this time. Also, make sure you did the geometry problems that start the UCO supplement based on what we did last time. And also, there's a separate geometry review. So there's 2 geometry reviews, one that's separate from the others, and one that's in the UCO homework supplement. Write it out all. And then today, do 5.1. That's these problems.
We don't turn them in anywhere, do we?
No, the homeworks are not to turn in. I should have repeated that again. Some people didn't get to all the things in the first day of class. The homework is not to turn in, it's to study for the exams, because all the exam problems will be very similar to homework.
Gotcha, thank you.
Okay.
Thank you.
Yeah. Have a good day.
Thank you. Have a good day.
I have a quick question.
Yeah.
So you said something about a quiz a few minutes ago. Is that like a weekly quiz?
I said it too fast, I guess. I said normally I give lots of quizzes, like a quiz between every exam to make sure everybody keeps up. I'm not doing this semester because it's too hard online to do that, but I might give an extra credit sometime.
Okay, thank you.
Yeah.